The laws of logarithms give us a way to either expand or compress a set of logs to suit our needs. A lot of times we're going to be using the compressing of logs in order to simplify an equation in order to solve it. But solving equations is in the next section. For right now, we're going to talk about expanding and compressing and evaluating. So here are three very important laws of logarithms. The first one being that the log base a of ab is equal to the log base a of a plus the log base a of b. So when two things are being multiplied in a single log, it's the same as separating them into two logs that are being added. The log base a of a over b is equal to the log base a of a minus the log base a of b. So two logs that are being divided in a single log can be separated into two logs by subtracting. And the last one, the log base a of a to the c power, that exponent can get written in front of the log and be multiplied in order to simplify it. In this first example, let's evaluate each of these expressions. So the first one, the log base 4 of 2 plus the log base 4 of 32 can be simplified into a single log, noticing that there's a plus sign between the two logs. We're going to write it as the log base 4 of 2 times 32, which is 64. Now we've already done evaluations of logs. What I had told you to do was set it equal to x, and then in order to solve this, we're going to rewrite it as an exponential equation. 4 to the x equals 64. So 4 to what power gives you 64? It doesn't take a long time playing in your calculator to realize that 4 to the third power is 64. In b, the log base 2 of 80 minus the log base 2 of 5. Since this is a subtraction sign between the two logs, we're going to rewrite it as a single log by making it the log base 2 of 80 divided by 5, which is 16. We're going to set that equal to x, and then rewrite it as an exponential function in order to solve it. So it's 2 to the x equals 16. 2 to what power is 16? Well, it's 2 to the fourth. And the last one, negative 1/3 log of 8. We're going to rewrite that as the log of 8 to the negative 1/3 power. Well, 8 to the negative 1/3 power is 1/2, so you end up with the log base 10 of 1/2. Well, the nice thing about the log base 10 is that we can use the log button on our calculator. So all I have to do is put in log of 1/2, and it'll tell you it's approximately negative 0.301. Now let's use our laws of logarithms to expand each of these expressions. So log base 2 of 6 times x. When you have multiplication, you can expand it by writing it as the log base 2 of 6 plus the log base 2 of x. And that's all we're going to do. There's no evaluating going on. They only asked us to expand it. So we're going to use those three properties to expand everything as much as possible. Now let's look at b. The log base 5 of x to the third times y to the sixth. So the first thing I'm going to do is going to write this as the log base 5 of x to the third plus the log base 5 of y to the sixth. Now I want you to notice that there are some exponents. And the laws of logarithms tell me that I can take those exponent and multiply in front of the log. So this is going to become 3 times the log base 5 of x plus 6 times the log base 5 of y. And that's as far as I can expand it. In c, the properties of logarithms also work for natural logarithms. So in order to expand the natural log of ab over the square or the cube root of c, first, the a times b in the numerator means that there's going to be addition. So we're going to have, I'm going to run out of space here, the natural log of a plus the natural log of b minus the denominator, because that's what you do with fractions, the natural log of the cubed root of c. Now remember that a cubed root is the same thing as an exponent of 1/3. So I need to get that exponent in front of the natural log. So the final answer is actually going to be the natural log of a plus the natural log of b minus 1/3 the natural log of c. And that's as far as we can expand it. Now let's go the other direction. Let's combine 3 times the log of x plus 1/2 times the log of x plus 1 into a single logarithm. What you're going to do when you go this direction is first you're going to get rid of numbers that are in front of the log. So first this is going to become the log of x to the third plus the log of x plus 1 to the 1/2. Now that I got rid of the numbers in front of the logs, now I notice that there's a plus sign between the two logs, which means that I'm just going to multiply them. So I'm going to write this as the log of x to the third times x plus 1 to the 1/2 power. There is no other simplifying that you need to do. There's no distributing, no nothing. Leave the answer just like this. Now let's combine one that's a little bit lengthier. Let's combine 3 natural log of s plus 1/2 natural log of t minus 4 natural log of t squared plus 1 into a single logarithm. First, we're always going to get rid of numbers in front of the log. So first this is going to become the natural log of s to the third plus the natural log of t to the 1/2 minus the natural log of t squared plus 1 to the fourth. Next, since these two are being added, we're going to multiply. So we're going to get the natural log of s to the third t to the 1/2. Since this part over here is being subtracted, that's going to go in the denominator. And that's all you need to do in order to simplify it. If you want to write t to the 1/2 as the square root of t, you can do that, but you don't have to. You can leave the answer just like this. Hermann Ebbinghaus came up with a logarithmic formula that explained the phenomenon of the law of forgetting. When you learn something and then you don't use it for a long time, you know you forget it. Well, there's a way of determining how much you will have forgotten or how fast you are forgetting using this formula. So if a task is learned at a performance level p sub 0, then after a time interval t, the performance level p satisfies the equation log p is equal to log of p sub 0 minus c times the log of t plus 1, where c is a constant that depends on the type of task, and t is measured in months. Please notice that it says months. Solve for p, and if your score on a history test is 90, what score would you expect to get on a similar test after 2 months, after a year? Assume that c is equal to 0.2. So let's start with a. They want us to solve this for p. In order to solve this equation for p, you first need to combine the left-hand side of the equation into a single log. Now, in order to do that, you first have to get rid of any numbers that are being multiplied in front of the log. So first, the log of p is going to equal the log of p sub 0 minus the log of t plus 1 to the c power. Then, since it's a subtraction problem, we're going to rewrite it as a single log as p sub 0 over t plus 1 to the c. Then I have a single log on both sides of the equation. But what happens to the logs? They cancel. So you're left with the equation that p, the performance level, is equal to the initial performance level divided by the time in months plus 1 raised to the c power. So now, in order to do the second part of the problem, if you know that you new 90% of a test. And that you want to know what you're going to do on a test in 2 months. And C is 0.2. I can just shove this now into my calculator and evaluate it. So 90 divided by 3 raised to the 0.2 is approximately 72. So after 2 months, I'd still get a 72. How about after a year? Well, this time, for the time, I would put in 12, because remember, T is in months. So now I'm going to do 90 divided by 13 raised to the 0.2 in my calculator, and then I decide that P is 54. So after a year, I'd still know 54% of the material. The last thing I need to talk about is something called the change of base formula, because you know that the log button on your calculator is only base 10. Well, what if I want to evaluate a problem that has another base? Well, turns out that we can use this thing called the change of base formula. Now, if you have a calculator with a new operating system on it, under the math function is a log function where you can actually just type in the base, type in the number, and it does the problem for you. But if you don't, then in order to evaluate the log base 8 of 5, you would do the log of 5 divided by the log of 8. So what you've done is you changed the base of the problem to 10. Now, it turns out that if you did the natural log of 5 over the natural log of 8, you would get the exact same answer, which is kind of cool. Because the way the change of base formula works is you just need to change the problem so the base in the numerator and denominator are the same. But we want to change it to a base that we can plug into our calculator. So you either need to use LOG or LN. But it's a pretty easy formula to use. If instead I wanted to evaluate the log base 9 of 20, again, you could choose to either do the log of 20 divided by the log of 9, or you can do the natural log of 20 over the natural log of 9. Notice that when you use the base change formula, the log of the base is always in the denominator, and the other number goes on the top. So this is what you would get if you evaluated that log. So what if you wanted to graph a log whose base was something other than 10 or e? In order to graph the function f of x is equal to the log base 6 of x, you would have to change this to the log of x over the log of 6. And when you type it in your calculator, it's going to kind of look like this. You're going to need to use parentheses. Then the graphing calculator will graph it for you. And again, it's your choice. It doesn't matter if you use LOG or LN. The graph you get will be the same.